You know the moment. Thumb on the button, half a second of nothing, and in that half second, your brain runs the worst-case scenario. Is this the day it doesn't come back? Then the logo blinks on and you exhale like you just landed a plane. Here's the thing. That half second isn't nothing. It's not loading. It's a full, furious relay race happening at a scale you cannot see, involving electricity, tiny pieces of software, and a supercomputer-sized decision tree, all finishing before you've even let go of the button. In the next few minutes, you're going to understand exactly what your phone does in the fraction of a second after you press power. And honestly, it's a more complicated sequence than launching some rockets. So, what actually happens in that gap, the one between your thumb pressing down and the screen lighting up? We're going to follow one tiny electrical signal on its journey through power delivery, hardware checkups, and a full operating system waking up from what is, electrically speaking, a coma, all before you can blink. This isn't the 60-second version you've seen before. We're going step by step in the actual order it happens, because the order is kind of the whole point. Let's press the button. The trigger, a switch with a very important job. Your power button is not smart. It doesn't know what an operating system is. It doesn't know what an app is. It's a mechanical switch. When you press it, you're just closing a tiny circuit, letting a trickle of electricity flow somewhere it wasn't flowing a moment ago. Think of the power button as a doorbell, not a light switch. It doesn't turn anything on directly. It just rings a bell inside the phone and says, "Someone's here." The chip that answers that doorbell is called the Power Management IC, or PMIC, and it is, without exaggeration, the single most important chip you've never heard of. Myth bust. Number 1. A lot of people assume the power button directly controls whether the phone is on or off. It doesn't. Even when your phone looks completely dead, several tiny components, including the PMIC itself, are technically awake, sipping a trickle of power, just listening for that doorbell ring. Your phone is never fully off unless the battery is physically disconnected or fully drained. Power delivery, waking the electrical nervous system. Once the PMIC hears the doorbell, its job is deceptively enormous. It has to take the messy, unstable voltage coming out of your battery and turn it into several clean, precise different voltages for different parts of the phone. Your processor might need 0.9 volts. Your display might need 3.3. Your camera sensor wants something else entirely. Feed any of them the wrong voltage and you don't get a slow phone, you get a dead one, possibly permanently. Picture the head chef expediting orders during the dinner rush, except every dish needs a completely different exact temperature, and if the temperature's off by a fraction, that dish is ruined for good. The PMIC doesn't just flip one switch, it sequences power to dozens of components in a precise order because switching everything on simultaneously would cause a voltage spike that could damage the hardware. Processor first in stages, memory next, storage after that, radios and sensors brought online only once there's something for them to talk to. This entire sequencing process from doorbell to stable power across the board takes only milliseconds, but it has to happen in exactly the right order or nothing downstream works at all. The bootloader is the tiny program nobody talks about. Here's something most people never think about. Your phone's operating system, Android, iOS, whatever you're running, cannot start itself. It needs something to load it into memory, check that it's legitimate, and hand it control. That something is called the bootloader. The bootloader is stored in a small, dedicated chip separate from your main storage, and it's the very first piece of software that runs before Android, before iOS, before anything you'd recognize as your phone. If your phone were a stage play, the bootloader is the stagehand who shows up hours before the audience arrives, unlocks the doors, checks that the sets aren't on fire, and makes sure the actual performers have somewhere to stand. The bootloader's job is narrow but critical. Locate the operating system's kernel. Verify it hasn't been tampered with using cryptographic signatures, and load it into RAM. On most modern phones, this verification is a real security boundary. It's part of what's called a chain of trust, where each stage checks the next before handing off control, so malicious code can't simply insert itself early in the process. The hardware checkup. Nothing proceeds until everything reports in. Before your phone lets any real software take charge, it runs a rapid-fire diagnostic pass across the hardware, verifying that RAM is responding correctly, that the storage chip is readable, and essential sensors and radio hardware are present and answering. This is conceptually similar to what desktop computers call post or power-on self-test, though on phones it's leaner and largely invisible. This is the equivalent of a pilot's pre-flight checklist, except the pilot here is a few lines of low-level code, and the checklist runs in milliseconds instead of minutes. Fuel? Check. Instruments? Check. Radios? Check. If any critical piece fails to respond, the boot process halts right there, which, incidentally, is one of the more common reasons a phone gets stuck on a logo screen instead of finishing startup. Kernel initialization. The deepest layer takes the wheel. With the hardware verified, the bootloader hands control to the kernel, the innermost core of the operating system, and the only piece of software that talks directly to your phone's physical hardware. Everything else on your phone, every app, every service, every swipe gesture, ultimately goes through the kernel to actually do anything. If the operating system is a country, the kernel is its entire infrastructure ministry all at once. It manages roads or data pathways, the power grid or energy distribution to components, and air traffic control, which process gets to use the processor and for how long. Nothing moves without going through it, and it makes thousands of these decisions every single second without you ever knowing. At this stage, the kernel initializes memory management, sets up communication between hardware components and software, and starts the very first user space process, essentially the ignition point for everything you'd recognize as the phone turning on. The boot animation. The logo is lying to you a little. Now we get to the part everyone actually watches. The logo, the spinner, the little animated flourish. Here's the myth bust worth knowing. Myth bust number 2. That animation is not the system loading a progress bar. It has no idea how far along anything actually is. It's a looping visual placeholder, a purely cosmetic layer that plays while dozens of background services spin up completely independently of it. The animation could finish its loop 50 times before the phone's actually ready, or the phone could finish loading while the animation's only halfway through one cycle. There's no real connection between what you're staring at and what's happening underneath. Behind that logo, the system is mounting the file system, essentially unlocking the warehouse where all your apps and data live and making it readable while simultaneously starting core services, the process manager, the display compositor that will eventually draw your home screen, network handling, and security frameworks. It's less a progress bar and more a beautifully decorated curtain hiding a stage crew working in a controlled frenzy behind it. OS and UI loading. The home screen finally arrives. Once core services are running, the operating system starts layering in everything that makes the phone feel like your phone. System services initialize, things like account syncing, notification handling, and background task scheduling. Then comes the launcher, the actual visual home screen app, which draws your wallpaper, your icons, your widgets, and hands you back control. Only at this exact moment, after power delivery, bootloader verification, hardware checks, kernel initialization, and service loading, does your phone actually respond to a touch. Everything before this point happened without your input mattering at all. The fun systems beat, what you don't see. Here's a number that tends to surprise people. By the time your home screen appears, a typical modern smartphone already has somewhere between 100 and 300 individual processes running quietly in the background. Location services, network daemons, security monitors, app update checkers, none of which you asked for by name, all of which the OS decided you needed before you even unlocked the phone. And there's a meaningful difference between a warm restart and a cold boot, which most people use interchangeably but shouldn't. A warm restart, the kind you trigger from the power menu, often skips or shortens several of the hardware checkup stages because the system already trusts that the hardware was working correctly a moment ago. A cold boot, starting from a fully powered-off state or a hard reset after a crash, runs the full sequence from the very beginning, doorbell and all, because the phone genuinely doesn't know what state anything is in anymore. That's a real part of why a full power off and on can sometimes fix problems that a simple restart doesn't. It's not magic, it's just a more thorough checkup. So the next time you press that button and hold your breath for half a second, remember that in that gap, your phone ran a full electrical wake-up call, verified its own software, checked every piece of its hardware, booted the deepest layer of its operating system, and loaded a couple hundred invisible processes all before that logo even finished its first loop. Turns out the scariest half-second of your day is also the busiest half-second your phone will ever have.